On February 19, 2025, Microsoft unveiled a quantum processor the size of a fingernail that operates on an entirely new state of matter, 8 qubits, fits in the palm of your hand, and they claim it can scale to 1 million qubits on a single chip. That is not a typo. 1 million. On a wafer, you could slide into an existing cloud data center. Every other quantum computer on Earth requires a warehouse. 5 weeks later, Google Quantum AI published a white paper proving that the encryption protecting every Bitcoin wallet, every bank transfer, and every military communication on the planet can be broken with 20 times fewer qubits than anyone previously thought. Not 20 million physical qubits, fewer than 500,000. And the private key behind your cryptocurrency? Cracked in approximately 9 minutes. Nation-states are already stockpiling your encrypted data right now, harvesting everything today, waiting for the quantum machine that will decrypt it tomorrow. This is not science fiction. This is a countdown. And the clock just accelerated. What Majorana 1 actually is: every major quantum computer built today, by Google, IBM, IonQ, Quantinuum, uses qubits that are catastrophically fragile. Superconducting qubits decohere from minor temperature shifts. Trapped ion qubits operate too slowly for practical scale. Photonic qubits cannot reliably interact with each other. All of them require between 1,000 and 2,000 noisy physical qubits just to produce a single stable logical qubit through brute force error correction. That overhead is why no one has built a useful quantum computer yet. Microsoft abandoned all of those approaches. They spent nearly 2 decades developing a completely different kind of qubit, a topological qubit, built on an entirely new material they invented called a topoconductor. It is a hybrid structure of indium arsenide semiconductor coated atom by atom with superconducting aluminum. When cooled to near absolute zero and exposed to precisely tuned magnetic fields, this material forces electrons to fractionalize into exotic quasi-particles called Majorana fermions, particles that are their own antiparticles. The quantum information is not stored in a single fragile particle. It is distributed across the entire topology of the system. Local noise cannot collapse it. Computations are performed by physically braiding these Majorana modes around each other. And because non-abelian anyones retain a quantum memory of their exchange history, the logic operations are intrinsically fault-tolerant. Microsoft's Chetan Nayak, technical fellow and VP of quantum hardware, described it as inventing the transistor for the quantum age. The result: topological qubits need only 5 to 6 physical qubits per logical qubit, compared to 1,000 or more for Google and IBM. Microsoft's proprietary 4D geometric error correcting codes deliver a 1,000-fold reduction in quantum error rates. And unlike conventional systems requiring complex analog microwave pulses, Microsoft's qubits are controlled digitally via simple voltage pulses, functioning like a standard light switch. That simplicity is what allows the chip to fit inside a standard server rack. The claims were formalized in a peer-reviewed paper published in Nature on February 19, 2025. The key experimental result: a single-shot interferometric measurement of fermion parity with an assignment error probability of just 1%. The system detected the difference between 1 billion and 1 billion and 1 electrons in the nanowire. The state remained stable for over 1 millisecond under a 2 Tesla magnetic field. Satya Nadella put it bluntly: all the world's current computers operating together cannot do what a 1 million qubit quantum computer will be able to do. Why this is terrifying. Every secure digital transaction on Earth, every bank wire, every military communication, every cryptocurrency wallet, is protected by public key encryption. RSA 2048 and elliptic curve cryptography rely on one simple fact: classical computers cannot factor astronomically large numbers or reverse elliptic curve math in any reasonable time frame. To brute force a 2048-bit RSA key using every supercomputer on the planet would take billions of years. A quantum computer running Shor's algorithm does it in hours. Shor's algorithm places the system into a superposition of states, essentially sending an entire search party into the maze simultaneously. Incorrect paths destructively interfere. The correct path amplifies. The key is extracted in polynomial time. A problem requiring billions of years becomes solvable in minutes. In 2019, Google estimated that breaking RSA 2048 would require 20 million physical qubits running for 8 hours. That felt safely distant. Then, on March 31, 2026, Google Quantum AI published a white paper recalculating the resources needed to break Bitcoin's 256-bit elliptic curve encryption. The new number, fewer than 500,000 physical qubits. A 20-fold reduction, and the time to crack a private key from an exposed public key, approximately 9 minutes. Bitcoin's average block confirmation time is 10 minutes. That leaves a 1-minute window between a quantum attacker stealing your funds and your transaction being confirmed. An estimated 6.9 million Bitcoin, roughly 1/3 of the total supply, sit in wallets where the public keys are already exposed on the blockchain. Those funds are a massive, immobile bounty, vulnerable the instant a machine powerful enough comes online. Harvest now, decrypt later. Here is the part that should keep you awake tonight. The threat is not waiting for Q-Day. It is already happening. Intelligence agencies across the world, China, Russia, Iran, North Korea, and Western agencies, including the NSA and GCHQ, are actively intercepting and stockpiling massive volumes of encrypted data right now. They record VPN traffic, copy encrypted email archives, siphon classified communications. They cannot decrypt it today, but they are banking on the certainty that a future quantum machine will. This is called harvest now, decrypt later. And it means that every piece of data with long-term strategic value, trade secrets, defense blueprints, multi-decade intelligence, transmitted via legacy encryption today is already compromised. CISA, the NSA, and NIST have all issued explicit warnings. The data is being collected. The clock is running. On August 13, 2024, NIST finalized the world's first post-quantum cryptography standards after an 8-year evaluation. Crystal's Kyber for key exchange, Crystal's dilithium for digital signatures, and Sphinx Plus as a mathematical backup. The NSA's CNSA 2.0 mandate requires all new U.S. national security acquisitions to support quantum-resistant algorithms by January 1, 2027. Full enforcement. Every piece of legacy encryption decommissioned by 2035. The skeptics. Before anyone declares the encryption apocalypse imminent, there is a critical asterisk on Microsoft's claims, and it involves academic fraud. In 2018, a research team led by Leo Keuvenhoven at TU Delft, working under Microsoft's Quantum Lab, published a paper in Nature claiming to have found definitive evidence of the Majorana fermion. It triggered massive excitement. Then 2 former colleagues requested the raw data and discovered that the researchers had selectively cropped graphs and deleted data points that contradicted the central claim. An independent investigation found severe confirmation bias. Nature fully retracted the paper in March 2021. That retraction haunts the Majorana 1 announcement. Sergei Frolov, one of the physicists who exposed the manipulation, has publicly called Microsoft's topological claims essentially a fraudulent project. Henry Legg of the University of St. Andrews published a preprint arguing that Microsoft's verification protocol is prone to false positives and exhibits gross cherry-picking of data. And Nature itself appended a rare editorial caveat to the 2025 Majorana 1 paper, explicitly stating that the results do not represent evidence for the presence of Majorana 0 modes. No independent lab has replicated Microsoft's claims. The global quantum race. Skepticism aside, the race is accelerating on every front. Google's 105-qubit Willow chip achieves 99.97% single-qubit gate fidelity. IBM broke the 1,000-qubit barrier with Condor and is targeting 200 logical qubits by 2029 with their Starling system. IonQ's trapped ion roadmap targets 2 million physical qubits and 80,000 logical qubits by 2030. Quantinuum demonstrated 12 fully fault-tolerant logical qubits after a $300 million funding injection and is pledging a universal fault-tolerant system by 2030. And then there is China, an estimated $15 billion in state funding. A 12,000-kilometer quantum key distribution network integrating 145 nodes with 2 satellites. The Zhuchangji 3.0, a 105-qubit superconducting processor that the USTC team claims runs 1 million times faster than Google's published benchmarks. The US responded with the $280 billion Chips and Science Act. The EU mobilized a €1 billion quantum flagship. The UK committed £2.5 billion over 10 years. Microsoft's own roadmap has 3 levels. Level 1, creating and measuring noisy topological qubits, is officially accomplished with Majorana 1. Level 2 targets stable error-corrected logical qubits using a 4x2 tetron array. Level 3 is the endgame, a fault-tolerant quantum supercomputer with 1 million topological qubits. They are operating under a DARPA contract and claim they will build a fault-tolerant prototype in years, not decades. Whether the physics supports that claim is the single most consequential open question in computing. What breaks if encryption falls? If a cryptographically relevant quantum computer comes online, the damage is not theoretical. The SWIFT interbank network becomes vulnerable to fraudulent wire injections. Industrial SCADA systems managing national power grids can be intercepted and hijacked. Electronic health records are exposed. A February 2026 report by the City Institute modeled a scenario where a single quantum-enabled cyber attack against a major U.S. financial institution could trigger between $2 and $3.3 trillion in cascading economic damage. The global cost to migrate digital infrastructure to post-quantum standards is estimated between $28 and $42 billion. For the U.S. federal government alone, the White House projects $7.1 billion just to upgrade civilian agencies by the 2035 deadline. Google has set an internal target to complete full post-quantum migration by 2029. The NSA's CNSA 2.0 mandates are already in effect, and 6.9 million Bitcoin are sitting in wallets with exposed public keys, waiting. So here is where we stand. Microsoft built a quantum chip on a new state of matter that needs 5 to 6 physical qubits per logical qubit instead of 1,000. Google proved encryption can be broken with 20 times fewer resources than anyone thought. Nation-states are harvesting your encrypted data right now. NIST finalized post-quantum standards. The NSA set a 2035 deadline. And the scientists who exposed the last Majorana fraud are calling this one a cherry-picked illusion. Either Microsoft just invented the transistor for the quantum age, or they are the biggest false alarm in computing history. Either way, the encryption protecting your bank account, your medical records, and 6.9 million Bitcoin has a confirmed expiration date. Ethereum Foundation researcher Justin Drake put it starkly after seeing Google's white paper. His confidence in Q-Day arriving by 2032 shot up significantly, estimating at least a 10% chance that a quantum computer recovers a private key from an exposed public key by then. The director of USC's Center for Quantum Information Science, Daniel Lidar, summarized the stakes. If you can eliminate almost all decoherence, you have nailed the holy grail of quantum computing. But so far, there is no consensus that Microsoft's results have pinpointed the observation of a Majorana.